Well, hey y'all. So we're back, and today we're going to look at some applications for exponentials and logarithms. But before we do that, I want to start with a question. What is this? Like right here. It's okay, don't freak out. There we go. What is this? Does anybody know? There you go. It's a fossil. Yeah. Okay. So do you know what kind it is? Well, I'm pretty sure it's something called an ammonite. You look it up. An ammonite kind of is circuitous, like a ram's horn, and it's a nice little spiral. And this is the piece of it. Very cool. I like fossils. I really like rocks. Here's another one. This is not an ammonite. Can you see? Okay, so it's heart-shaped. Also looks like a butt, which is weird, like an animal butt. Ah! Anyway, now you can't unsee it. But here's the cool thing. Look right here. Isn't that awesome? So it's like, I don't know, a little wormy thing right there. Yeah. So this is heart-shaped. And I'm not exactly sure what this is. I have some other that are heart-shaped, but they're this way. So they're more, this one is broken, but the backside came out kind of like this, okay? I'm not exactly sure what this is. I looked up, I used to know what this was called. This is from Texas, from when Texas was all underwater. And we used to know what this is called. My husband actually found this out on some property that belonged to his parents. But anyway, cool stuff. Somebody said, oh, it's a sea urchin. I'm like, I don't really think it's a sea urchin. But anyway, this is an ammonite. So long story short, these are fossils. What do fossils have to do with algebra 2 and logarithms? So glad that you asked. Well, if I were a geologist, I could figure out how old these are using, guess what? Logarithms, okay? Carbon dating, you've probably heard of it. Carbon is in all life, and carbon's number is 12. And if we take and can measure how much carbon is in a substance, we can determine its age. So carbon 12 and carbon 13, the isotope carbon 13, is actually very stable, but carbon 14 is very unstable. And we know that through testing that the half-life of carbon 14 is about 5,700 years, plus or minus 40. That would be the margin of error. So knowing the half-life of carbon, we can measure how much carbon is in a substance left, and then work backwards by taking a logarithm to figure out how old it is. Really pretty cool. So that is one of the applications that we're going to be looking at today is carbon dating, all right? We are going to be in section 7.8. So we are in 7.8, and this is essentially, we are using base E and natural logs LN. So it's applications, because this is what everybody wants to know. When are we ever going to use this? Okay, well, in just about any ology that you might be in, biology, sociology, psychology, financial growth, population control, just populations in period, and then we'll end up by looking at the logistical model. You can follow along pretty much in your book. There's an example in the book. I won't work that example. I will work one similar to it, so you'll have all kinds of examples to go with. So we're going to start out. There are two formulas given to you in your book on page 509, one for exponential growth and the other for exponential decay. They are identical, except for in exponential growth, the K or growth constant is positive. And in exponential decay, there is a negative sign in front of the growth, in front of the constant, right? So for us, with our example on half-life, half-life is going to be a decay problem, right? So the half-life of a substance is the time it takes for half of the, oh, come on, pen. Half of the atoms of a substance to disintegrate. And we usually refer to half-life in things that are radioactive. All right. So your book looks at some a carbon-14 problem, and then after that, then we use those values. We can. So we're going to look at actually the half-life of plutonium, which is a controlled substance for nuclear war purposes, of course. So the half-life of plutonium 2, oh my stars, this pen, 239. All right, now plutonium 239, that is a number, okay, like carbon 14, that's the isotope number. Plutonium 239, that is the name of the plutonium isotope, right? It's heavy, okay, like carbon 14 is heavy. So plutonium 239 is the name of the isotope. And the half-life of plutonium 239 is 24,000 years. So that's one of the reasons why it's so dangerous, y'all, is because look, it's going to take 24,000 years for half of that poison to go away. 24,000 years. I mean, that's just like redonkulous, okay? That's a long, long time. So that's why it's very dangerous. Because if we have one El Stupido do something with plutonium, then like the whole world is going to disappear, or it'll be like The Road. Have y'all read The Road in English language arts? Or maybe you saw the movie. But yeah, it's like world nuclear war, whatever. And then how long is it going to take the world to recover? Thousands and thousands, right? Millennial years. All right. So the half-life of plutonium-239 is 24,000 years. Now it says find the value of K. All right. So you're like, wait, I don't even have an equation. Well, you're right. It's in the book, but we'll write it out for you. So when we're talking half-life, we're always talking decay. We're not talking growth, right? So we're going to use the decay formula, which is over here. And it says F of T, it might say Y, same thing. F of T equals A times E to the negative KT power. And what is this? Let's talk about who all these variables are. Well, A, just like before, A, that's that amount at time 0, right? Which is the initial amount. How much did we have at the beginning? Okay. E is E. That's Euler's constant. It's approximately 2.8, but you're going to use E on your calculator. You're not ever going to put in 2.8. No bueno, okay? You're going to use E on your calculator. T is the time. And that could be in years. It might be in minutes. Some elements are so volatile that's in seconds, but T is time, all right? So we already know our time, 24,000, right? We don't know the initial amount, do we? F of T is essentially what? How much do you have left after time T? In other words, what's Y? What's our amount? What do we have? Amount left after time T. And then K is our constant that represents continuous growth or decay. And when it's negative, it's decay. We would have the same equation that you see when you look in your book. It's the same equation when it's positive. When K is positive, it's growth. When you have minus K, it's decay, right? All right. So this is the equation that we're going to be using for most of this unit or this section. So what do we know? So let's do that. What do we know? Right? What do we know? Well, according to this, the half-life of plutonium-239, 239 is the name of the isotope. It is not a number to use in the equation. All right. What do we know? 24,000 years. Which is that? F of T, A, T, K, no, T. All right. We know the time is 24,000 years. And you're like, Cosgrove, we don't know enough stuff. Look at all these. Look, there's 1, 2, that's not a letter, okay? That's Euler's constant. 3, 4. There's 1, 2, 3, 4 variables. How are we going to solve this equation? Because we just know one thing. Well, really, you know more than that. All right, so what do they not tell you? A. What else do they not tell you? F of T. Okay. What are we trying to find out? K. Because that's what they, so that means that this problem is expecting us to know A and F of T. It's expecting us to know that. And we're looking at it, we go back and look, and we're like, what the crap? I don't see it here. And you don't. You're right. So how much did we have at the beginning? All of it. We had all of it. However much was there, we had all of it. Okay. So when they don't tell us how much, we had all of it, right? So we'll come over here. Somewhere is a little note. I'm going to come down and change color. And I'm going to put a star down here. And I'm going to say, understood A is 100%, that's all of it, or 1. How much did I have at the beginning? All of it. Okay, 1. After 1 half-life, how much was left? So if I started with all of it, and I've had 1 half-life, how much is left? A half. Yeah. So when A is understood 1, then after 1 half-life, F of T is what? A half. Okay. So let's come back up here. How much did we have? Not 239. That's the name, okay? How much did we have? All of it, 1. After one half-life of 24,000 years, how much was left? Half. Okay? All right. Watch out for that. Some people get tripped up. I'm trying to find K. So let's fill in our equation. So I'm going to say 0.5. Okay, this is the equation that I'm using right here. So half equals my initial amount, 1, times E. Remember, that's not a variable. That's Euler's constant. I don't know K, to the negative K times T, which is 24,000. All right, I'm going to work this sucker back to figure out K. Notice where K is. It's in the exponent spot. How do we get variables out of the exponent spot? You're going to have to take a log, right? But not yet. We want to isolate it. So that means if there's anything added or subtracted over here, we got to eliminate that. If there's anything multiplied or divided to the E, we got to eliminate that. And then we can rewrite it as a log. Okay? All right. So obviously multiplying by 1 doesn't affect things, but we can rewrite it. 0.5 equals E to the negative K times 24,000. All right, so now I have E to the stuff equals number. I'm ready to rewrite or put it in log form. So I'm going to say the ln, okay, right? We're going to logify here. The ln, or natural log, of 0.5 equals negative K times 24,000. And now to solve this, I'm going to divide both sides by 24,000. Actually, yeah. I'm going to go ahead and divide by negative 24,000 if that's okay with you, to save me one step at the end. All right, this is straight up calculator. So on your calculator or on your TI calculator that you should now have on your laptop, you're going to say the natural log of 1/2 and close the parentheses, and then divide by negative 24,000. So it's going to look just like this. And then hit enter. All right, so you see that 2.8 e to the negative 5. Okay, so remember that is scientific notation for times 10 to the negative 5. And I'm going to have to round, so I'm pulling out my approximations here instead of equals. And I'm going to say 2.8811 times 10 to the negative 5th. And that, we found, is the decay constant that represents continuous decay for plutonium-239.